Hello everyone, and welcome to this video where we will explore additional tools offered by the Vision software. And today we will focus on the IQ probe that performs the trace IQ recording for the post-processing of EVM or ACPR or etc. like in measurement process defined in AMCAD IQSTAR software. The IQ probe will be capturing the input signal that will be generated by the AWG-IWF source, and that would be amplified by Unilateral amplifier model. You can find the template I'm using here for this tutorial in template schematic, and you can come and select the IQ probe schematic and slide it into the schematic editor. This template is fully customizable, allowing you to modify it as needed. It also includes predefined formulas to calculate the final integration time and the number of time points. It also includes variable assignments here in the equation block. I will explain the variable assignments afterward in this tutorial. We will begin with the IWF source, which generates signals using IQ waveform files exported from the waveform generator application I'm showing you here after their creation. And for the source, we need to define also the signal average power that here I'm defining as a variable that I'm gonna sweep in the var block. And I'm also defining the internal impedance as 15 ohm for this source. And going back to my schematic, we will be generating the IQ waveform file that will be used here in the source. And to do this, we'll go to the waveform generator application, and we're creating a 16 QAM signal with a symbol rate of 15 and an oversampling factor of 4. This results in a signal with 200 megahertz bandwidth, which is suitable for my power amplifier model. Once the signal is generated, we'll review its general parameters, which will also appear in the AWG-IWF source. And additionally, we will note the PAPR value, which helps set the average power input to the source. It's important to ensure that the sum of the injected average power and the PAPR remains below the maximum power limit of the model. Next, I'm gonna demodulate the generated signal to show you the 16 QAM constellation. And since the file is ready, I'll export it. Gonna replace this signal, for example. And I'm gonna go to the system architect and to the source, and I'm gonna select the path to the file I have generated. And I'll revisit the waveform informations here that I'll be using to calculate the final integration time of the simulation. I am copying the sampling rate and I'm putting it here in symbol rate 100 exponential 6. Then I validate for me to keep the value. Then I'm also taking the number of points, which is 8,000, and I'm putting it in the number of sample. Here I have already done that, but I'm doing it again with you. And I select. And as I said, we're using these variables from the equation to calculate the final integration time as well as the number of points. And going back to the source, I'm also specifying the internal impedance as 15 ohm, and defining the signal's average power as a variable. I'm calling P in dBm. And after validating, I'll move to the variable block and define my input power variable. I've already put it here, but I'm gonna modify it with you. I'm gonna put the same name here, and as well as a nominal value of -13, and we're gonna sweep within a range going from -13 to 0.5 with a number of points going to 10. And these values are in fact related to my power amplifier model, where it's this one. I've extracted it. And if we go to the data, we can see that the range of the input power of maximum input power of the power amplifier goes from minus 13 to about 8 dBm. And going back to my schematic, I'm also declaring the carrier frequency of the HPA model I have inserted here. And I'm declaring it as a variable. So it's called FC. And after validating, we're going to the variable block. And this is the FC variable I'm declaring with a nominal value of 1.185. And we're sweeping within a range going from 1.185 to 1.375. With 3 points. And this is also related to the model. You've already seen it, I guess, but we have a model of centered around 1.28 gigahertz and with a bandwidth of 200 megahertz. The UHF model, or the unilateral high-frequency amplifier model used, works with a fixed input and output impedance and focuses on frequency dispersion effects within the operational bandwidth. And we can visualize the detailed description of the model in the affiliated documentation of the software, or even on the documentation in our website. And I can show it to you, which is this one, describing in detail the model. And this model actually focuses on frequency dispersion effects within the operational band, and it employs amplitude to amplitude modulations and amplitude to phase modulation conversions for signal analysis. And it is used for applications like radar and constant envelope signals. In this case, we will use this model with a 16 QAM signal to highlight nonlinear distortion by measuring the EVM and ACPR of the output signal. So, to the schematic, we've added 2 additional probes, which are wave meters that provide us with the incident and reflected power at each side of the HPA, which are data required by the IQ probe, in addition to the PDC of the power amplifier and the carrier frequency. We've also configured the simulation control to transient simulation mode, as well as an analysis type of nested sweep analysis. It is also worth mentioning that we have added a 15 ohm resistance to the end of the simulation to ensure an accurate calculations, since we are using waves. However, this load does not affect the model because it's unilateral. And once everything is set, we can proceed to run the simulation as shown here. As we can see here, the simulation is quite fast. It took 2 seconds. Yes, and it is creating the IMX, the results, and we can come and visualize the results provided by the IQ probe. But for a deeper analysis, we can export the IMX in the data source to visualize and analyze with more specific metrics such as the EVM ACPR in the whiteboard. Moving to the whiteboard, we are creating a new page. I don't prefer an A4, a portrait page. I prefer a landscape. It's preference or use. So I've created my page, and here I have my file, results file in the data sources. But also in this data source I have lots of data sets, 3 data sets. And the one I'm really needing, and the one that contains the data I want to analyze, is the data set named prob IQ. So I'm gonna come and filter the data sets. As you can see here, it's gray because I have both vision simulation and the modulated power sweep one tone. I'm gonna remove this one because I'm interested in this one, and I'm gonna choose variable. And for the data, I'm gonna choose dataset name, and I'm gonna apply. And here you can see that I have prob IQ as a dataset name filter. To this, I'm gonna add another variable, which is F0, the center frequency. And here are my filters. After that, the goal is to visualize results. So I'm gonna create a graphic. And this graphic will take as source the filter and not the data sources. I'm gonna close this one to have more space. Here you can see that in level we have F0, and in data we have lots and lots of data. I'm gonna start with the ACPR. I'm gonna put the ACPR, lower ACPR. I'm gonna plot it as a function of the available power. And to be more familiar, I'm gonna plot it dBm. And here's my lower ACPR. Other than ACPR, another thing that we can plot, and that is very useful in the analysis, it's the we can start by the EVM, RMS, and we're gonna plot the average one. Other than the EVM, we can plot the compression, the gain compression. Click on apply, and a final parameter that we can plot is the most obvious one is the output power, and I bet it's at the end. And these are curves, but what is more relevant and what's more worth analyzing are subcurves of these curves. So I'm gonna create a new page, and in this in this page, I'm gonna create a graphic, of course. And this graphic is not gonna take the filter or the data source as source. It's gonna take the graph one, which is the lower ACPR one. And as we can see, the allowed curves here is empty. So to fill it, we have to come and select a certain point from the lower ACPR and refresh in here. We find the allowed curves. And here we have different levels of data. IQ data, spectrum, AM, EVM, and other plenty of other ones. I'm gonna start with the IQ level, and I'm plotting I'm gonna start with this one. I'm gonna plot the output apps envelope as a function of time. And for a better visualization, I'm gonna remove the markers and I'm gonna make it bigger. And this is our absolute power voltage. In addition to the app's output power voltage, I'm also adding the input one. Gonna first put it on the same axis, and it's the reference apps envelope. And for the color policy, I'm gonna choose one by data just to visualize them with a different color. And here we can clearly see the difference in amplitude between the two. The green one is the reference apps envelope and the red one is the output apps. I'm gonna change the axis to right, apply. Then I'm gonna zoom in just to show you that the two signals we are observing have very similar shapes. Next, we are gonna plot the spectrum. Now we're copying this one. And here in the level, we are choosing spectrum. The representation would be as a function of the normalized frequency, and we are representing the normalized raw power, the output, and then the reference. Then click on apply. This is our spectrum. If you here notice that both spectrums are centered around 0 megahertz, it is normal since the frequency is normalized. But what we really need to observe here is the spectral regrowth between the two. Aside from the spectrum, another important representation is the constellation. So we'll go ahead and plot it. I'm gonna copy this one. I'm gonna change the dimensions of this plot. I'm gonna 515 just to have like a square plot because I'm plotting the constellation. I'm gonna go to the level. Gonna remove this data. Go into the level, and I'm plotting first the reference constellation. And put in reference constellation in both. Then plotting the imaginary, the real and imaginary part. Here, you are noticing that we don't have dots, so we're gonna remove the lines and then click on apply. This is the reference constellation, and we can come and compare it to the constellation we have generated earlier, and we can see that it is quite identical to the one we have generated. To this reference constellation, I'm adding the career one. So I'm gonna name this layer reference, and I'm gonna give it a unique color, red, for example. I'm gonna also give it a unique shape. I'm gonna leave it square. I'm gonna apply, and then I'm gonna add a new layer. I'm gonna name this one career, and I'm choosing career in Constellation, doing the same thing and representing real and imaginary parts. I shouldn't forget to remove the line display and give it a unique color. I'm gonna give it a bright green to visualize it well, as well as a bit of shape cross plus, for example. And here we have the representation of both the career and the reference. If I zoom in a bit, we can see that the uh, the green ones, the career ones, are a bit translated from the reference. This is due to the non-linearity of the power amplifier. And this is where the EVM's role comes to calculate the distance between the reference and the career constellation symbols. And to complete this analysis, we are adding another graphic. I'm gonna reduce this this one here. I'm gonna go down to add another graphic, which is AM representation. I'm gonna copy this one here, and in the level, I'm removing this data, and in the level, I'm choosing AM. And I'm plotting it as a function of the available input power. And if I plot it like that, you're gonna see it this way. But what we are gonna do, we're gonna plot it as dots and select bold like this. And to have a representation of the density of the symbols, we're gonna add the density option to it. And here we can see and visualize clearly the density of the symbols. So in the constellation, we start from the center, then we increase the power and obtain the first circle here that corresponds to the line in yellow here, and then increasing the power, we obtain the second circle with the most density of time samples that is represented here in red, and then the external circle after increasing the power, we obtain this line in orange with the time samples corresponding to the external circle. In this part of the IQProp tutorial, I'm going to use the same schematic I've used earlier to simulate the UHF model. And this time I'm going to use the HPA-U-HFLF model. And if we go to the documentation of this model, we can see that it's a unilateral amplifier model featuring fixed output and input impedances fixed to 15 ohms. And contrary to the UHF model, it captures both high and low frequency memory effects caused by the interaction through bias circuits, for example, thermal behavior, trapping effects in GaN technologies, and operating band dispersion. Its identification process includes one-tone and two-tone characterization to model these effects. And this comprehensive model is suited for various applications, including radar and wideband systems, although it excludes load impedance variations. The next thing we are going to do is extract the model of the UHF-LF HPA. And to do that, we are going to the Device Modeler application, and we are creating a new device, new, and we are choosing as a model UHF-LF, and naming it UHF-LF tuto, and OK. And when it comes to the data needed to extract the model, one-tone data file containing the HF information, then the two-tone data file containing the LF measurement or simulation data. And how to obtain the measurement or simulation data will be explained in more details in a separate video, as well as the extraction model. And for now, what I'm gonna do is I'm gonna put these parameters that will give us a good model. And I'm gonna put 3, 3, and 6 for these orders. Another thing to note is that if wideband is not already selected, we have to choose wideband model technology, then proceed to extract the model. And in this part, we'll be looking directly at the graphs and assuming that the extraction is correct. And we'll concentrate on showing what the model can yield in the simulation. Here's the one-tone extraction as a function of the input power and the frequency, as well as the parametric gain as a function of the input power as well, and the frequency. The next step, as I did before, is to use this model in the system architect schematic, and I'm putting it in the HPA block. So I'm choosing the model I just extracted and validating by clicking on OK. And for a better visualization, I'm going to use a different signal. The input signal is a 10 mega band signal with a number of points of 20,000, and I'm going to show it to you in the waveform generator. I viewed these parameters to generate the signal. It's a 16 QAM signal, just like the one I've used for the UHF, with a symbol rate of 10 and a symbol count of 5,000 and an oversampling factor of 4, which gives us a 10 mega hertz bandwidth and a point count of 20,000. And since we have used a different signal, we have to change the parameters in the equation block, especially the number of points in the sampling rate. So the number, I have changed it already. The number of samples, I've changed it to 20,000 and the sample rate to 14 mega. I'm still simulating with a solver, with a data flow solver, and a sweep analysis type is done. For the variable block, I'm actually fixing the frequency at its nominal value, which is 0.83 gigahertz, and sweeping the input power from minus 13 to 10 with a number of points of 20. And that's it for the changes. I'm gonna launch the simulation. It's really quick. I'm gonna close it, and here it is generating the results file. After obtaining the IMX, I'm gonna slide it to the data source and visualize the results in the whiteboard. So I'm sliding the IMX, which is the result. file containing the 3 datasets, and then I'm going to the whiteboard. I've created a new page, and just as I did before, I'm gonna add a filter that's gonna filter the dataset. I said before that I'm most interested in the prob IQ dataset, so I'm filtering using the variable data, and I'm filtering using the dataset name, and it shows the prob IQ. And another variable, just as I did for the UHF, is the F0. Okay, I'm gonna make it bigger. Then I'm gonna display the results. The first thing I wanna do is choose my filter, which is filter 2, as a source for the graph. Then I'm gonna represent the output power as a function of the available input power. So it's being available, and its unit should be dBm. Then we're gonna represent the output power. Other than the output power, I'm gonna have to represent the lower, and upper ACPR, which are 2 key elements for the analysis of the performance of a high power amplifier. And as the first one, I'm gonna use filter 2 as a source. Then I'm representing as a function of the available input power, and of course I'm adding the lower ACPR first, then the upper one. And to distinguish between the two of them, I'm gonna apply a one data by layer. And here we can see that the upper and the lower, when in this frequency, are not symmetrical. We are going to compare the ACPRs between the UHF-LF and the UHF model. Afterwards, I'm just going to add another representation, which is the spectrum, which is going to be subcurve of the output power. So it's going to take the graph 2 as a source, graph 2. And since we have not selected yet a point, it does not have a curve, a log curve. And if we go and reset, here we can see that the curve had appeared. And what we are gonna represent is a spectrum, so the level would be spectrum. And I'm gonna make this one bigger, and we're gonna represent it as a function of the normalized frequency. And this is the normalized raw power reference, and I'm gonna add the output too. I'm gonna remove the markers, and also choose one color by data. And here is the ACPR. We can clearly see that there's an asymmetry between the left and the right. The same asymmetry you see in the ACPR. And I'm gonna return to the system architect and redo a simulation with the same number of points in order to for us to compare between the UHF and the UHF-LF model. So going back to system architect, I'm gonna select the UHF simulation, and I'm gonna change the input signal into the same one I've used for UHF-LF with 10 megaband. And with this number of points and 14 for sampling rate. I'm gonna change it. It's the same one, 20,000, and for this one, I'm gonna change it to 14 mega. I'm just gonna verify. Okay. Okay. So we are still doing a sweep analysis with data flow solver, as well as fixated on the central frequency and this input power band. I'm gonna simulate real quick. Then export the results into the data source. And going back to the whiteboard, here we can see clearly the results for both simulations. And if I come and unselect the UHF-LF, we can see here the results for UHF-LF. And for example, here we can see clearly a symmetry between the upper and lower ACPR, as well as a symmetry in the spectrum. But if I come and select the UHF-LF to compare them, then come and select both of them here. I will select both of them, yes. And here, if I come and choose one color by data set, then yes, then we can clearly see that here the upper and lower ACPR of the UHF model is symmetrical, while the other one is asymmetrical. Same thing for the spectrum, one by data set. And we can, yes, we can see the asymmetry in the one in red. And this is due to the fact that UHF-LF is a model with memory, in contrary to the UHF, which is a model without one. All these nonlinearities that are taken into consideration by the model affect the performance and the efficiency of the system we are working with. That's why there are methods to alleviate or counter these effects, and one of them is the digital pre-distortion. And I'm going to show you a schematic that I've prepared for you. I'm going to go to System Architect, and then this schematic. So here we have the same modulated source that I've used in the previous simulations, as well as the same modulated signal. Also, I will be using the same HPA-U-HFLF model. To this model, we've connected an API. An API is a block that allows us to do a co-simulation with another external system simulator. And in this case, it's a MATLAB API, so it's going to help us to do co-simulation with MATLAB, executing a script that is located in this directory. To this MATLAB API block, we give an input signal, this one, as well as certain parameters that are gonna be used in the script that's executed. And these parameters are given values or declared in the equation block. Then we are getting an output after the execution or the run of the script behind this MATLAB API. So the script is a DPD signal processing function that allows us to apply DPD before the high power amplifier. Other than the DPD API, we have also another MATLAB API that allows us to align the signals at different steps of the schematic, and also calculate an estimation of the coefficients of the DPD with each iteration. And other than the MATLAB APIs, we have probes like the gain probe that allows us to visualize the RF gain, as well as the average power added efficiency probe, and of course the ACPR probes. Then to these probes we've added several scopes, spectrums, and waveforms. And the next step would be to start the co-simulation between Vision and MATLAB, and to do that we click on Start Server. If in some cases Start Server doesn't work, you can always force restart MATLAB. So in my case I'm gonna start server, and then MATLAB opened, and here I can clearly see the co-simulation is running in MATLAB. We're gonna close this one, and we can already go and run the simulation in Vision. I'm gonna replace the previous result. And here the simulation is done, and we have the results of the simulation. But for better analysis and visualization, I'm gonna export the result file and visualize it in the whiteboard. I'm gonna create a new page, and if we open the data source, we can see here several data sets. So I'm gonna use a filter to filter the data sets, and the first variable for the filter would be dataset name, and we can come and choose a dataset as we wish. Other than the dataset name variable, I'm gonna add a filter, but this one it's gonna be a data, and it's the step variable. It allows us to choose the which iteration to visualize the output signal after the DPD for each iteration. This is for the first, this is for the second, and we can carry on like that. So I'm gonna add a graphic, and what I want to show you, that also would be the most obvious, is the spectrum. I'm gonna represent as a source, I'm gonna choose this filter, which is filter 3, clear reset. And for the data, I'm gonna do representation as a function of the frequency, and I'm gonna represent the first the input spectrum, and I'm removing the markers, and second it's the DPD PA, I'm sorry, PA, the PA spectrum. And to see better, I'm gonna do it one by data, and here it should be on the left to be able to see the amplification of the signal. So this is the first iteration without DPD, and if we increase, we can clearly see in green that the spectral elevation is decreasing in comparison with the beginning. So here we can see a big elevation as well as an asymmetry between this and this part. Then increasing, we can clearly see the output signal after the DPD getting closer and closer to the input, to the form of the input signal, with low or less spectrum elevation.